Hey everyone, today what we're going to do is talk about nuclear reactions and the two different major kinds. We've got fission and we got fusion. The first two slides are not within your area, okay? I'm going to show you where it's going to be at. So we have fission, this is your copy, and I've modified this a little bit that you're going to have to scroll down. And then you have my copy, that's my master copy. Now you guys are gonna pick up with fission and then go back on with fusion. If you notice that this gray part here, that is actually blocked out, so you guys are not doing it. You will do it on the next slide. And then we're gonna compare and contrast. Okay? So the first part is how is energy released from atoms? Now this is important because we do here in the state of Kansas receive energy from atoms. It's a very, I believe, useful and very fundamental part of our energy grid. Okay, so we are under the conglomerate of Evergy, which is part of Kansas City all through Kansas. Okay. Alrighty, so what particles make up the nucleus of an atom? These first two slides are review. The nucleus is composed of two subatomic particles. They are protons and they are neutrons. Protons and neutrons, right? And remember that the neutrons were like bungee cords. They helped keep that repelling protons not from expanding from each other. Okay? This is beryllium because we have 1, 2, 3, 4, and then we have 5. So its mass number is 9. Be atomic number is 4. Okay. What is an isotope of an atom? Well, this is an isotope of, I don't know what atom this is. Subtract 32. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14. So I'm guessing this is maybe nitrogen, no, silicon, and then these would have differing amounts. And if you see that this one's a little bigger than the other two. All right. Now that's important when we're dealing with isotopes, is that sometimes they become stable and unstable. I'm going to pause for. And by the magic of pausing and editing, that we are back at this site. So if you notice that if I have nitrogen, if I were to throw another, it's stable right now, it's stable still, but then it becomes unstable. Well, what if we have a really small atom and it goes, or a really big atom and it goes boom? What are the effects of that? We're talking about unstable atoms for the most part, especially when we're talking about fission, excuse me. Okay. All right, I'm going to go back to our side, and these can become unstable and they have to somehow become stabilized. So the first type of nuclear reaction is fission, and I'm going to, okay, we have fission. So this is where we're going to start on slide 1. Now, I have the topic question underneath red. So, the topic question is, what is nuclear fission and how does it happen? So that will go right here. Not fizzing, fusion. Okay. All right. Now the first slide I'm going to go through in step, and then you guys can go and move on with your own. Okay. when we start to fission. So I think you've got the process. Okay. So fusion stems from the Latin word to melt. So I already have that down for you guys, so you guys can see that here. Okay. Usually when you have a melting substance like an alloy, or if you guys have ever welded, you'll see these two kind of solid structures become liquefied. And so it means to and if you've ever had a solder for electricity, you'll see these, there's a metal that goes in and melts into the other, and it causes, then it cools, and it's a real strong structure. Okay? Structure. All right? So, with high temp and pressure, lighter nuclei become to form a larger nuclei. So, what is a nuclei? Well, we have the term nucleus. Remember, we're not talking about cells, we're talking about atoms. And a nucleus is basically the central part where we have protons and neutrons. Well, like fungus, that's one mushroom stem. But if I have a ring of mushrooms, it's actually called fungi. So it's the plural of nucleus. I know that sounds weird, but that's the way it is. I'm sure there's some English term that we could figure that out, or we could get Waldy or Shannon down here and figure it out. So the plural of nucleus is nuclei, like fungus and fungi. Okay? So with high temperature and pressure, lighter nuclei combine to form a larger nuclei. So that will go right here. With high temp and pressure, smaller nuclei form a larger, and I'm going to make sure that I'm telling you this right, nucleus. And that's key because we have two make one. So atoms are coming together. Okay. Okay, so sorry, I had to get something. Okay. Alrighty. With high temp and high pressure, there is going to be a lot of it requires a lot of energy to get it going, and but there's a trade-off with that as well. I'm going to apologize, and I want to get one more thing. Sorry, there's something important within that. Okay, all right. So where do these happen? It takes place on sun and stars. And there's one more key thing about this is if I'm fusing two elements together to make a new element, it's creating a new thing. We're going to come back to that probably tomorrow, that I want to stress something with you guys on this. Okay? All right. So that will go right here. All right. Okay, it needs temperatures of over 10 million degrees Celsius to get this started. So unfortunately, even though the core is hotter than the sun on the outside of the sun, our core, the Earth's core, it is not feasible to really do fusion here on Earth because it will take an insurmountable amount of energy to start it and to regulate it. Okay. So just give me a second. I have to make sure that. All right. Okay, so what I did is I went ahead and changed the coloring just a little bit between yours and mine so that you could see that this was on the next slide. So remember from here, what we have to have is a lot of temp, a very high amount, around 10 million degrees Celsius. Okay, so that is a tremendous amount of heat. And this also takes a great deal of pressure. Okay. And so you kind of will see this within here, well, within our thing. It takes a great deal of pressure and it takes a great deal of heat. And also right here is that we have these two hydrogen atoms. Now that's the one thing that they don't describe is we have, I'm going to put this right here, is that we have a hydrogen and we have a hydrogen. So I'm going to write that H and H. Now, how do we know it's hydrogen? Because it's one proton, one proton. And this is hydrogen 2. Okay? Alrighty? So, because it has one proton and one neutron. So, fusion is an isotope with hydrogen with a neutron called deuterium. Heavy hydrogen. Excuse me, it's hydrogen 2. Ooh. Hydrogen 2 is very heavy. Hydrogen or heavy water is very important in nuclear processes and nuclear bomb making. I'll let you write that down. Okay, the isotope of hydrogen 2 is called a heavy hydrogen. So it's 1, 2, 1, 2, correct? It has a neutron, which most hydrogens do not. Okay, whoop, excuse me. And so going back to that PhET diagram or that PhET isotope simulation, we have hydrogen 1. It's stable. Now deuterium or hydrogen 2 is stable as well, but it gets a little bit trickier and it's not very abundant. We can make it, okay? I just saw a documentary about the Nazis taking over Norway's production of heavy hydrogen. And so that, again, it is a very key part on nuclear weaponry. And then tritanium is hydrogen 3. So, but we have hydrogen 2, which is deuterium, and we need both of those. Now they can create it on the sun. That's another issue of why we have problems. Now those fuse together and make helium. So that was that alpha particle, that alpha particle when we were talking about the gold foil experiment. And so when I go here, it makes helium 4. Okay. The cool thing about this, and I'll show it to you, is there's no nuclear waste. Okay. No nuclear waste. They're trying to figure out a way we can do fusion within this because there is a problem of radioactivity seeping into the environment via the rods or the core melting down in fusion. All right, I'm going to make another video production. Bye, guys.